there are two fundamental things that are happening. The first is that the processor, the engine by which the computer industry runs on, the central processing unit, the performance scaling has slowed tremendously. And yet, the amount of computation we have to do is still doubling very quickly, exponentially. If processing requirement, if the data that we need to process continues to scale exponentially, but performance does not, we will experience computation inflation. And in fact, we're seeing that right now as we speak. The amount of data center power that's used all over the world is growing quite substantially. The cost of computing is growing. We are seeing computation inflation. This, of course, cannot continue. The data is going to continue to increase exponentially, and CPU performance scaling will never return. There is a better way. For almost 2 decades now, we've been working on accelerated computing. CUDA augments a CPU, offloads and accelerates the work that a specialized processor can do much, much better. In fact, the performance is so extraordinary that it is very clear now, as CPU scaling has slowed and eventually substantially stopped, we should accelerate everything. I predict that every application that is processing intensive will be accelerated, and surely every data center will be accelerated in the near future. The specialized processor can take something that takes a great deal of time and accelerate it down to something that is incredibly fast. And because the two processors can work side by side, they're both autonomous and they're both separate, independent that is, we could accelerate what used to take 100 units of time down to 1 unit of time. 100 times speed up, but you only increase the power by about a factor of 3. And you increase the cost by only about 50%. We do this all the time in the PC industry. We add a GPU, a $500 GPU, GeForce GPU, to a $1,000 PC, and the performance increases tremendously. We do this in a data center. $1 billion data center, we add $500 million worth of GPUs, and all of a sudden, it becomes an AI factory. This is happening all over the world today. Well, the savings are quite extraordinary. You're getting 60 times performance per dollar. 100 times speed up, you only increase your power by 3x. 100 times speed up, you only increase your cost by 1.5x. The savings are incredible. Why is it that it saves so much money, but people haven't done it for so long? The reason for that is because it's incredibly hard. There is no such thing as a software that you can just run through a C compiler and all of a sudden that application runs 100 times faster. That is not even logical. If it was possible to do that, they would have just changed the CPU to do that. You, in fact, have to rewrite the software. That's the hard part. The software has to be completely rewritten so that you could refactor, re-express the algorithms that was written on a CPU so that it could be accelerated, offloaded, accelerated, and run in parallel. Just last week, Google announced that they've put cuDF in the cloud and accelerate Pandas. Pandas is the most popular data science library in the world. Many of you in here probably already use Pandas. It's used by 10 million data scientists in the world. Downloaded 170 million times each month. It is the Excel, it is the spreadsheet of data scientists. This is Earth 2. The idea that we would create a digital twin of the Earth, that we would go and simulate the Earth so that we could predict the future of our planet to better avert disasters or better understand the impact of climate change so that we can adapt better, so that we could change our habits now. This digital twin of Earth It's probably one of the most ambitious projects that the world's ever undertaken, and we're taking large steps every single year. You can learn physics. You could teach an AI model physics. The AI model could learn the meaning of physics, and it can generate physics. We were scaling down to 1 kilometer, not by using filtering, it was generating. And so we can use this method to generate tokens for almost anything of value. We can generate steering wheel control for a car. We can generate articulation for a robotic arm. Everything that we can learn, we can now generate. We have now arrived not at the AI era, but a generative AI era. This AI factory is generating, creating, producing something of great value, a new commodity. In the late 1890s, Nikola Tesla invented an AC generator. We invented an AI generator. The AC generator generated electrons. Nvidia's AI generator generates tokens. Both of these things have large market opportunities. It's completely fungible in almost every industry. And that's why it's a new industrial revolution. Years, every single layer of computing has been changed. From CPUs, general purpose computing, to accelerated GPU computing, where the computer needs instructions, now computers process LLMs, large language models, AI models, Nvidia inference microservices. Now what happens is the NIM runs inside this factory, and this NIM is a pre-trained model. It's an AI. Well, this AI is, of course, quite complex in itself. But the computing stack that runs AIs are insanely complex. Inside this container is CUDA, cuDNN, TensorRT, Triton for inference services. It is cloud native so that you could auto-scale in a Kubernetes environment. It has management services and hooks so that you can monitor your AIs. It has common APIs, standard APIs, so that you could literally chat with this box. You download this NIM, and you can talk to it. So long as you have CUDA on your computer, which is now, of course, everywhere. It's in every cloud, available from every computer maker. It is available in hundreds of millions of PCs. When you download this, you have an AI, and you can chat with it like ChatGPT. All of the software is now integrated. And of course, as you know, we now have the ability to create large language models and pre-trained models of all kinds. And we have all of these various versions, whether it's language-based or vision-based or imaging-based, or we have versions that are available for healthcare, digital biology. We have versions that are digital humans that I'll talk to you about. And the way you use this, just come to ai.nvidia.com. And today we just posted up in Hugging Face the Llama 3 NIM, fully optimized. It's available there for you to try. And you can even take it with you. It's available to you for free. And so you could run it in the cloud, run it in any cloud. You could download this container, put it into your own data center, and you could host it, make it available for your customers. Most of the AIs today don't understand the laws of physics. It's not grounded in the physical world. In order for us to generate images and videos and 3D graphics and many physics phenomenons, we need AIs that are physically based and understand the laws of physics. This is Blackwell. Blackwell is in production. Incredible amounts of technology. This is our production board. This is the most complex, highest performance computer the world's ever made. This is the gray CPU. And these are, you could see each one of these Blackwell dies, two of them connected together. You see that? It is the largest die, the largest chip the world makes. and then we connect two of them together with a 10 terabyte per second link. Okay, and that makes the Blackwell computer. And the performance is incredible. Take a look at this. So, you see our the computational, the flops, the AI flops for each generation has increased by 1,000 times in 8 years. Moore's law in 8 years is something along the lines of, oh, I don't know, maybe 40, 60. And in the last 8 years, Moore's law has gone a lot less. And so, just to compare, even Moore's law at its best of times compared to what Blackwell could do. So the amount of computations is incredible. The amount of energy that is used has gone down by 350 times. Well, Pascal would have taken 1,000 gigawatt hours. 1,000 gigawatt hours means that it would take a gigawatt data center. The world doesn't have a gigawatt data center, but if you had a gigawatt data center, it would take a month. If you had a 100 megawatt data center, it would take about a year. And so nobody would, of course, create such a thing, and that's the reason why these large language models, ChatGPT, wasn't possible only 8 years ago. What's the miracle is this chip, this NVLink chip. People are starting to awaken to the importance of this NVLink chip as it connects all these different GPUs together, because the large language models are so large, it doesn't fit on just one GPU, it doesn't fit on just one node. We created an end-to-end architecture so that the NIC and the switch can communicate. And that generative AI is working with you, interacting with you, generating videos or images or text or maybe a digital human. And so you're interacting with your computer almost all the time, and there's always a generative AI connected to that. Some of it is on-prem, some of it is on your device, and a lot of it could be in the cloud. These generative AIs will also do a lot of reasoning capability. Instead of just one-shot answers, they might iterate on answers so that it improves the quality of the answer before they give it to you. And so the amount of generation we're going to do in the future is going to be extraordinary. However, Blackwell is here, and every single platform, as you'll notice, are several things. You've got the CPU, you have the GPU, you have NVLink, you have the NIC, and you have the switch. The NVLink switch connects all of the GPUs together as large of a domain as we can, and whatever we can't do, we connect it with very large and very high-speed switches. Our next generation platform is called Rubin. The Rubin platform, I'm not going to spend much time on it. I know what's going to happen. You're going to take pictures of it, and you're going to go look at the fine prints, and feel free to do that. So we have the Rubin platform, and 1 year later, we have the Rubin Ultra platform. This isn't the future. This is happening now. There are several ways that we're going to serve the market. The first, we're going to create platforms for each type of robotic systems. One for robotic factories and warehouses. One for robots that manipulate things. One for robots that move, and one for robots that are humanoid. And so each one of these robotics platform is like almost everything else we do. A computer, acceleration libraries, and pre-trained models. Computers, acceleration libraries, pre-trained models. And we test everything, we train everything, and integrate everything inside Omniverse, where Omniverse is, as the video was saying, where robots learn how to be robots. Now, of course, the ecosystem of robotic warehouses is really, really complex. It takes a lot of companies, a lot of tools, a lot of technology to build a modern warehouse. And warehouses are increasingly robotic. One of these days will be fully robotic. So a robotic factory is designed with 3 computers. Train the AI on Nvidia AI. You have the robot running on the PLC systems for orchestrating the factories. And then you, of course, simulate everything inside Omniverse. Well, the robotic arm and the robotic AMRs are also the same way, 3 computer systems. This is not science fiction, and it's being used all over Taiwan, and it's just really, really exciting. And that's the factory, the robots inside, and of course, all the products are going to be robotic. So there are two very high volume robotics products. One, of course, is the self-driving car, or cars that have a great deal of autonomous capability. Nvidia, again, builds the entire stack. Next year, we're going to go to production with the Mercedes fleet, and after that, in 2026, the JLR fleet.